Good afternoon and welcome to the Music and Technology Seminar at Carnegie Mellon. Our guest today is John Kolar, a multi-talented musician whose wide-ranging interests in game design, music composition, and art installations have led him to his thesis topic, which is centered on experiments with human auditory perception. John's thesis grew out of his work with Daniel Rosenberg Munoz, who was a seminar guest almost exactly a year ago on February 28, 2023. John Kolar is one of several students who became involved with Daniel's fascinating speaker array experiments as a result of hearing about them in our seminar series. As usual, please mute your mic until it's time to jump in with comments or questions. And now, please welcome John Kolar to the Music and Technology Seminar at Carnegie Mellon.
Thank you, thank you. So for those of you who don't know me, I'm John. Thanks for having me here. So I'm going to go ahead and share my screen. Can everybody see that?
Yeah.
Yep.
And then I'm going to hit share sound as well. So Ricardo recommended before I go to share a little bit of the music that I play. So this is about a minute snippet of my indie rock band Mother of Earl and a music video that we released about a year ago. If you are interested, here it is.
Inside, outside, upside down, a few more years in this border town. Can we grow old and dignified, or will we reach a familiar line? Wasted all my time and all my friends, think I lost my mind. It's bound to happen again. You know you show me you really don't care. So you head down 79 with the wind in your hair. May tell a lot of lies, but I tell them with conviction. Said you didn't mind my eyes, but I think you mind addiction. And the idiots speak, all eyes on me. My eyes on the prize, but only one left to see. 15 excuses that I won't use, and 14 threads that stick like glue, and 13 occultists must have cursed my name, and 12 more months for something to change. You know, I'll just rotate.
So there's a little snippet there of Mother of Earl. Hope you enjoyed. And also, let's see, this as well. Another shameless plug. I'm playing a gig this Friday in Shadyside at Shady Grove, 9 to 11. It would be just me, free entry. I'm playing some guitar, piano, and singing covers and originals. So if you're around and want to come, that would be great. So enough of that. I will start now with the presentation. So I'm John. I'm currently a second-year master's student in the Music and Tech program here. Oh, I just realized it's spring 24, not spring 23. Hopefully that's the only typo. But yeah, this is my thesis presentation. So the current working title for my thesis is the spatial analysis of a wavefield synthesis loudspeaker array for human auditory perception experiments. So here's a brief overview of the presentation. So I'll go into a little bit of the background in spatial audio, a little bit of the history. It might be review for a lot of the audio engineers here, but I think it explains the relevance of the project a little bit. And then it goes into the wavefield synthesis background, some advantages and disadvantages of wavefield synthesis and the applications that it has. And that'll lead into the motivation for the thesis, the initial work that I've already completed, the proposal, potential limitations, and the timeline and goals. So that's a little overview of what I'll be talking about today. And at any point, if you have questions, feel free to unmute or put it in the chat. There'll also be time for questions at the end. So spatial analysis, there's the title again at the top. And it's all regarding wavefield synthesis, or WFS for short, as you'll see within these slides. And wavefield synthesis is a spatial audio technique that utilizes an array of loudspeakers to render virtual acoustic environments by reproducing sound fields. So there's numerous applications across multiple industries for wavefield synthesis. And this presentation will outline a proposed methodology to analyze the acoustic performance of an array and to identify and characterize its strengths and limitations, especially when using this system for scientific experiments. So spatial audio, there's all types. Here's a few that are listed: stereo, a basic one, surround, ambisonics, binaural, Dolby Atmos, which is becoming more and more popular, and of course, wavefield synthesis, which we'll be talking about today. So there's advantages and disadvantages and limitations to all of these, and we'll get into them a little bit here. So this, I found this nice diagram in one of the papers when I was doing my literature review here, and you see all the types of spatial audio, and you have three main trees below it. You have the loudspeaker, stereophony, binaural technology, and wavefield reconstruction. So stereo, it's for your basic, also surround is in the left with different loudspeakers, and then you have binaural tech, which has the headphones, and then you have wavefield reconstruction that has two types of ambisonics and wavefield synthesis. And then this is a nice little historical perspective. So you have the patent for the first phonograph and gramophone in 1887, I should say, stereo being invented in 1931. And then you have ambisonics in 1970, binaural recording headphones in 84, wavefield synthesis in 93. And then within the past 20 to 25 years, you've had a lot of hardware and other computational devices to deal with the complex math that goes into a lot of these spatial audio types of spatial audio. So here we have your typical 5.1 surround on the right. Your green is your one sweet spot. At the top-down view, you have 5 speakers, 3 in front, 2 behind, and then the 0.1 is your subwoofer. So basically, if you're sitting in the center and it's tuned, that's where you're going to get some spatialization. Then we're talking about binaural here. This picture on the right is a Neumann KU100 binaural microphone. It's fairly cheap. It's only like $10,000 or something like this, but it has one microphone in each ear, and it's supposed to record sounds as they're heard by the human ear. And then you can play that back in headphones, and it's supposed to be a simulation of what your ears would be hearing in a specific environment. And it incorporates these two things called ITD and IAD. ITD is the interaural time difference, which is the difference in time between the sounds arriving at each ear. And this affects how we perceive the low frequencies. So the low frequencies have a longer wavelength, and they can bend around the ear. So they will be the same amplitude relatively at both ears if they can bend around the head, and they won't be absorbed by the head. So you'll hear them at the same amplitude with your both left and right ear if you have an off-axis sound source. But they will arrive at the ear at different times because the speed of sound is the same. So the time difference will help you to localize low frequencies. And then you have IAD, which is interaural amplitude difference. And this helps to localize high frequencies because your head will absorb the lower wavelength, higher frequency sounds, and that will decrease the amplitude of the higher frequencies. So if there's a sound coming from the left, your left ear will hear those high frequencies, your head will absorb them, and your right ear won't hear those high frequencies, and our brain can process that. And that's one way that we localize sound. Another thing that's heavily related to binaural is these things called HRTFs, head-related transfer functions. That's a mathematical model of a filter, a transfer function that incorporates how the head and body affect audible sounds. So the reflections and the absorptions off the shoulders and the body and the head, and how that affects everything. And then also pictured here is Shep's ORTF mic. And I've read that some audio engineers who prefer this stereo method, as I think Ricardo does, some people speculate that they like it so much because the spacing is very similar to the spacing of the ears. So it's a microphone orientation that somewhat simulates how we hear with our ears. So it's preferred by a lot of audio engineers. So those are the non-wavefield reconstruction types of spatial audio. And now we have these two with wavefield reconstruction. We have ambisonics and then underlined wavefield synthesis, which is what we're here to talk about. But before we talk about wavefield synthesis, we need to talk about what is a wavefield. So here's one one way that I like to think about wave fields. So if you have a spherical wave pictured here, this red dot would be a point source that would be emanating out equally in all directions. This is 2 dimensions, but you can picture it going up and down as if it's in a sphere, but 2 dimensions, it's just a circle. So it's radiating equally outwards in all directions. But then once you get far away from the source, you notice that the lines, if you keep looking at the same window, become more straight, more and more straight. So as you get far away from a spherical source, you end up with a plane wave. So straight lines up and down represent a plane wave, and then you have spherical waves on the left. So like so, on the left here is our spherical wavefront, and on the right is our plane wavefront. So the spherical wavefront is curved like an arc of a circle, and then the plane wavefront is straight up and down like a plane. So a wave field is the space that all of these waves are existing in and interacting within. So ambisonics determines these wavefronts using spherical harmonics mathematics, and it computes this wavefront that should be heard, and it reconstructs them through spherically spaced speakers. So you can see in this image on the right, this person is sitting in a concert hall, and they can emulate that concert hall sound for someone sitting in a room that's the size of that sphere, but they do the math to figure out, okay, well, if there were a speaker placed in the concert hall at that point, what would be coming out of that speaker? And they do that for all of the speakers in the sphere. And if you sit in that sweet spot, you can just be sitting in any old room with that spherical speaker configuration, and you can hear what the concert hall might sound like with all of the reflections off the walls and the absorption and the room acoustics properties of that room. But there's one sweet spot, and that's sitting in the center of that sphere. And these are 2 different types of ambisonic microphones. I think they look very funky. They just have several different diaphragms all in different locations, but those look cool. So now we'll get into the wavefield synthesis. Wavefield synthesis uses this old mathematical principle called Huygens principle. I think I'm saying that correctly. I've only ever read it. I've never actually heard it spoken, but I'm calling it Huygens. But this principle says that all points on a wavefront of sound, say it again, sorry. Okay. All points on a wavefront of sound can be regarded as new sources of wavelets that expand in every direction at a rate depending on their velocities. And this describes wave phenomena like diffraction, refraction, and reflection. So here on the left, I know that definition isn't super intuitive, so I made a little diagram to try to explain it. We have another spherical wave here on the left. But if you were to put points on that wavefront, they will become new point sources that emanate outward. So we put a point on each of those, and then we start to draw them as if they were point sources emanating outwards. Then the sum of those sources will give you the same wavefront at a later point in time, depending on their velocity. So basically, it's a way to break up a wavefront into a bunch of tiny different pieces, and it helps with describing these different wave phenomena. So now I'm going to leave the presentation for a second and kind of show Huygens' principle in this Java applet called Ripple. So it's this really cool applet here, and it just lets you draw point sources and other things, and you can do sound waves. So now I have the simulation stopped, but if I hit unclick the stop, it makes a wave, and you can change the speed of the simulation, the frequency, and all of that good stuff there. So you can do all kinds of different things here. That's what our point source looks like. And then what I want to show now is the single slit. So now we have this slit in a wall, and what's going to come from here is a plane wave from the top. So there's our plane wave coming in, and based on Huygens' principle, we can predict what's going to happen. So basically, everything that's all parts of the wave that are going to hit this wall are going to reflect backwards, except for the part that's going through this slit. And what's going to happen at the slit is it's going to look like a point source. So if I put a point source there, it emanates outwards. And then once the plane wave gets there, it looks very similar to the point source. and emanates outwards, right? So that's just one confirmation of Huygens principle in this little ripple demo. I really like this ripple. You can just do ripple applet. I guess right now it was visible light, but either way, it just deals with all different types of waves. You can look at all kinds of different interesting things, different modes, beams, shifts, refraction, all kinds of fun stuff. So I think it's a really cool tool to visualize waves in general. So now I'll go back to the presentation. So what if we made these point sources loudspeakers? Then we would have wave field synthesis. So that's what I'm going to talk about today. Here is a picture of a wave field synthesis loudspeaker array. You can see the flower, the white flower looking circles are the drivers, and then below them, those are the ports. And it's a linear array with several speakers. So say our source was a violin or some musical instrument, it would be emanating outwards. And what if we had two of those and we put a linear array of loudspeakers? You can kind of picture how those two violins would be emanating radially. And if you have this linear array of loudspeakers and you use wave field synthesis, that array of loudspeakers can reproduce a wavefront from multiple sources. So there's three different types of sources that the wave field synthesis can utilize, can reproduce. So there's the point source, which is on the left. That would be where the point is above the speakers in this image or behind them. And then you have a plane wave coming in at an angle behind it. And then you can also put a point source situated inside of the listening area. So this is a little video demonstration of the first with the point source behind the speakers. And in this case, the speakers are on the left and the sound would be emanating to the right. So that is a point source behind the speakers, emanating outward to the right. So there's that one. And then we have similarly with the plane wave emanating from behind the speakers to the right. And that looks more like a linear line straight up and down, unlike the sphere before from the point source. And then lastly, we have a point source, but in the listening area. So this one looks a little bit more complicated, but it will look like what looks like a point source, but originating from in front of the speakers instead of behind the speakers. So, and you can see the response time at the top after so many milliseconds. So it's happening much, much faster than this. It's a slowed down simulation. So wave field synthesis is good for all three of these types of waves. And here are some advantages to wave field synthesis. There's no single sweet spot, unlike a lot of those other spatial audios. So this allows the listener to move freely around the listening area, and you can place sonic objects in an environment as long as it's within the listening area. Wave field synthesis can also create an accurate recreation of real acoustic environments. And when you allow sound artists to use it, it's great for creating abstract acoustic environments that aren't real and may be obvious, but you don't need to use headphones. There are some disadvantages. It's expensive. You need a lot of loudspeakers and you need a lot of equipment, wires, amplifiers, networked audio. It's a complicated setup. So it's not necessarily consumer friendly. You see a lot of it in research institutions or in universities, though, in types of labs. Also, just like any system, it's susceptible to room acoustics. So it works best in an acoustically treated room, and it's not mobile because it's so big. It can be mobile, but it's just not super easy to move. So here's some of the applications. We have virtual augmented reality, game design, music composition, art installations, scientific experimentation, and architectural acoustics. So here are some examples that fall into those categories. This is a classroom at the Technical University of Berlin, and it just looks like a normal classroom until I point out that this is a linear array of loudspeakers that goes all the way around the classroom. And I think there's something like 600 loudspeakers in this room. So I'm not really sure what they use that for in class, but it must be a crazy place to learn in Berlin there. This is a listening room at the University of Salford in the UK. and they place the loudspeaker array above. They hang it from the ceiling, and I'm assuming that those speakers are somewhat angled down towards the listener in that sweet spot. So that's an interesting use of it. You can see those diffusion panels on the ceiling. So it's an acoustically treated room. And then this is the Arup Sound Lab. They have a wavefield synthesis array behind the screen, and they combine ambisonics and wavefield synthesis. So I had the chance to work with Arup as an intern this past summer. They have sound labs in several of their offices. But Arup's an architectural acoustics firm. They do a lot of architectural engineering type things, but they have an acoustics and audiovisual division, and they use this type of spatial audio to render what a space would sound like before they have to build it or before they have to renovate it, so they can bring a client in and let them hear what it would sound like before they decide how much or what type of acoustic treatment they want. So that's a pretty cool application of these two types of spatial audio. And then also here at Carnegie Mellon, we have this wavefield synthesis array in the Spatial Experiences Lab, the SXL for short, which is in Margaret Morrison 127. And very soon, the Pittsburgh Children's Museum will have one as well, built by the team here at Carnegie Mellon. So that will be installed, I think, in the coming months, and there will be an interactive exhibit there, which will be fun. So this is the SXL lab, and if you saw Daniel's presentation last year, then this might be a little bit of a review, but basically there's an infrared camera tracking system. So there's, I think, 10 or 12 cameras mounted to the ceiling, and you can see in the top left corner picture. In the bottom left corner picture, you see those mugs, and they have the dots on them, and then behind it is the computer screen for the tracking. So that camera system can track those objects within the room. There's also a projection system you can project onto the ground, onto the walls and the floor and the ceiling. And then there's also this 64-channel wavefield synthesis loudspeaker array. And all these systems can communicate with each other, so you can really create some spatial experiences. You can have a sound like it's emanating from an object in the room. You move it around, and the sound will follow it. You can also track an object and use it to draw something on a screen or a flashlight using the projection system as well. And at the appendix A at the end has a technology diagram showing these connections if you're more curious. So recently, there has been approval for an auditory perception experiment at CMU. That's a collaboration between the auditory lab and the Department of Psychology, which is led by Dr. Lori Heller, and the Spatial Experiences Lab, which we just showed, in the School of Design, which is led by Dr. Daniel Rosenberg-Munoz. So these two are collaborating on an experiment that's titled Naturalistic Multimodal Interactions, the Effect of Motion on the Integration of Hearing, Vision, and Knowledge. So this auditory perception experiment is going to use the wavefield synthesis system and use it to experiment. So this experiment is going to look at the ventriloquist illusion. So if you don't know what that is, it's when a voice appears to originate from the puppet and not from the speaker. So on the left, we have the ventriloquist, and then on the right, we have the puppet in that picture. So because the puppet's mouth is moving, to our eye, we may perceive that the source location of that sound to be closer to the puppet, even though the sound is not coming from the puppet. And this is replicable in a lab setting if you just have a discrepancy between an auditory and a visual stimuli, like they do in this ventriloquist illusion. And their previous experiments have shown that the perceived location is biased towards the visual stimuli. So if you see something moving, you're more likely to think that it's also making a sound. Another aspect that this collaborative study at CMU is going to test is the semantic knowledge about audiovisual pairing influences and how that influences the location bias. So if you think that a specific visual item is supposed to make a specific sound, if it doesn't make the sound that you're anticipating, that's the semantic meaning behind that sound. And if those two don't match, then there will be another location bias similar to the auditory visual stimuli discrepancy bias. So in this perception experiment at CMU, they're going to experiment with the ventriloquist effect threshold. So what's the distance between the perceived location and the source location based on a combination of different experimental situations. If you have moving or stationary auditory and visual stimuli. So they'll do that, and they'll study the semantic meanings of effect. On sound localization, for example, if you are expecting a moo to come from a cow, but instead it's coming from a horse, how does that affect where you localize it? And this is a picture of a possible experimental scenario with that wave field synthesis array in the lab. So we have those green and blue eggs that are being tracked. In the future, we would like to make those, figurines with cows and horses. And if you have a neigh sound coming from the cow on the right, how does that affect what you're hearing and where you locate the sound? So that will be included in this perception experiment at CMU. And this experiment is planned to be completed by the end of the year. And it's going to be fully reliant on the wave field synthesis system in the lab. So because of that, it's going to be necessary to investigate the current state of the loudspeaker array. Since it will be used for science, you have to ensure the validity of the experimental data, and you need to better understand the system's strengths and weaknesses so that you can interpret your data once you get it from the human perception standpoint. And not only is it necessary to understand how the loudspeaker array is performing, but it's also necessary to understand the room acoustics that the array is in, and you can determine the effects of the room on the performance of the wave field synthesis system. So that's a little motivation for the thesis. So more motivation, I guess, is that it would be a foundational study to characterize the overall performance of the system, and this study will enable the future work when using this system for various applications, also outside of scientific experiment applications. So before understanding the proposal, it's important to understand some of the limitations of wave field synthesis. And if you understand and identify these limitations, it can inform the methodology for testing the performance. So here are three of the well-known common limitations to wave field synthesis. They are spatial aliasing, the truncation effect, and like other audio systems, it is also susceptible to room acoustics effects. So we'll break these three down in the upcoming slides. So spatial aliasing, it's very similar to normal audio aliasing, except it just implies a spatial element. So in this image on the bottom left, this is spatial aliasing that's occurring when you're trying to draw a triangle, but the grid system would be the pixels on the screen. So if you don't have a fine amount of pixels, it will make the triangle look jagged just because you don't have enough resolution. So this is this undesired distortion. In the wave field synthesis sense, it's an undesired distortion caused by position-dependent narrowband breakdowns in a frequency response within the wavefront range. So you can reduce this distortion by decreasing the distance between adjacent drivers in the wave field synthesis array, because sound is a spatial phenomena as well, and each frequency has its own wavelength, so those wavelengths are related to the spacing between the drivers. So if you put the drivers closer together, then you'll be able to get a higher spatial aliasing frequency. This may not have a significant effect on our experiment, considering the individual driver's frequency response, but it's just something to consider. And this is at RPI, at MPAC. I forget what MPAC stands for, but this is the University in New York. It's their, computer music society organization there. They have this wave field synthesis array that they're, I think, currently constructing, or maybe it's already constructed, but you can see that in the middle, those white flowers are the drivers, and then above them and below are the ports. So basically they have two of the arrays, but they have them on top of each other, and then they're shifted at half distances from the drivers. So they're kind of staggered there, and that gives you a closer distance between those drivers, which would increase the spatial aliasing frequency. So another limitation is the truncation effect. So the wave field synthesis wavefront assumes that the speaker array is infinite, but it cannot be, unfortunately. So this leads to artifacts at the array's physical boundaries. So where the array ends, there's a shadow wave effect that's caused by this truncation, which causes a distortion in the reproduced sound field. So this is not something that we can avoid, but it's just something to understand with the limitations in understanding how that's going to affect our acoustic data. And with our array at CMU, it has 64 loudspeakers, and we're not planning to increase the size of that at any point. So that's what we're working with. Also, wavefield synthesis is susceptible to the effects of room acoustics. So wavefield synthesis can produce complex wavefronts that are independent of the room where the speakers are located. And the array functions best when it's placed in a room with a lower reverberation time, because then you're hearing more direct sound and less reverberated sound. So they're minimized. The effects are minimized when you treat the room with absorption and diffusion, and they're minimized when you're closer to the listening area. And here's a little diagram on the right, where the guitar player on the left would be the wavefield synthesis array, and the listener on the right. If you increase the amount of direct sound and decrease the amount of reverberated sound, then it will stay truer to the actual spatialization of the wavefield synthesis array. So that's another limitation to the system. So I completed some initial testing on the system, and this is going to outline what I did. This is a top-down view of the Spatial Experiences Lab. You can see the door in the top left, the windows in the bottom. The wavefield synthesis array is labeled, and then that blue triangle is the spatialization range. And what I did is I chose some measurement locations, which are in the top right, and some source locations, which are in the bottom right. And I took an analog SPL sound pressure level meter, and I placed that at the 9 measurement locations at the same height of the loudspeakers and pointed towards the array. And then I had 3 source locations. So a trackable egg that was pictured before was placed at those 3 locations, and that was emulating the sound source using the wavefield synthesis array. And I used max MSP to send pink noise through the system at those source locations, and I measured them. So each measurement location or each source location making 27 total combinations. And here are those measurement and source locations a little bit blown up for you to see there. And here's a photo. So I used a music stand that had that SPL meter on it. That was measurement location 1, and then source location 1. So you see that the SPL meter is pointed towards the array at the same height of the speakers, and then the source is that blue egg on the left. And the source did not need to be at the same height of the loudspeaker, because the system recognizes, well, I guess the wavefield synthesis can only spatialize in the horizontal plane, not vertically. So I wanted it out of the way of the speaker so it didn't affect the measurements there. And here are the results. So each measurement location has these dBA values, and the dBA values are color coded on the right. So you have the highest being green, medium being yellow, and the lowest being red. So when the source was in the left corner, as we would assume, it was loudest there, right? So we have the green closest to the left. And then similarly, as we go through the sources, source 2 was also in the middle. We have the green in the middle, so it was loudest where the source was. And then similarly on the right, source 3 on the right, it was also loudest close to the source. So that was good. It was a sanity check measurement that showed in conclusion that the array is undoubtedly spatializing the sound. Within that spatialization triangle zone, the maximum sound pressure level difference was 12 dBA, which is significant because the distance from the array to the point of the triangle is only about 12 feet. So if you're getting a 12 dBA difference within that small triangle, it's good, and that's definitely discernible for a human subject with normal hearing. So this was the initial work, and it's going to function as a great starting point, but there are still several remaining aspects of the system to investigate. So this is when I will start to talk about the thesis proposal. We want to do some wavefield synthesis performance measurements. So it'll be my job to design and implement an acoustic testing methodology that will utilize many, many more source and measurement locations with the necessary spatial resolution for scientific experimentation. And I will similarly conduct these experiments with no object within that spatialization triangle. And I'll limit the objects in the room to reduce acoustic interference, absorption or reflection. And then I will again place the measurement device at the same height as the drivers in the wavefield synthesis array, and we'll be using a sound pressure level meter or a measurement microphone, or both. But we want to get some spectral processing as well within this measurement. So based on previous literature, humans have a minimal audible angle of perception of less than 2 degrees in the horizontal plane, and the horizontal plane is shown in the bottom left. But that's when listening in anechoic conditions. That study was completed in an anechoic chamber. So we are not in anechoic conditions in the spatial computing lab. So we're predicting that it'll be about a 4 degree or 5 degree minimum audible angle of perception. So with that in mind, we want to implement enough source locations to determine the performance against that threshold. So here's another top-down view of the lab. We have a measurement position, seating position in the orange there, and then we have that angle in the purple pink color. We want to change that angle and choose our source locations so that we have multiple different angles that we can choose from, and that it's granular enough so that it will mimic how humans can hear in that horizontal plane. So this is a photo of the SXL and the room acoustics. It's a rectangular room, and it's got concrete floors and fairly high ceilings, so it's got a long reverberation time and fairly loud background noise. So it's unideal. The room acoustics there are unideal, which is going to be something that we'll address in this thesis research, but also it's just going to be a struggle in general with dealing with those effects. So I plan to also, in addition to doing the measurements of the system, I'll also do some room acoustics measurements with impulse responses to gather spectral information on the room's reflections and absorptions, and we can determine the room modes and any treble frequencies. And we'll analyze these reflections and interpret the data and recommend acoustic treatment upgrades. And I'll do this to mitigate the effects of the room acoustics and enhance the spatialization performance. And on the right, you can see that's just a normal living room, and that plot representing the frequencies that exist and the modes that are excited within that room. So I'll do some similar analysis to kind of help visualize the room and the treble frequencies that exist within it. And then after completing that, I will repeat all of these measurements with the same system in the Vlahakis studio control room. So Ricardo has generously approved of me using the system, or using the room, bringing the system in to do some measurements there. And I will use the exact same source measurement location pairs, same equipment, same system. And I will also repeat the room acoustics measurements in the Vlahakis studio. And the benefits of doing it in the control room is that it has a really short reverberation time compared to the spatial computing lab, and it's an acoustically controlled environment. And then when I have both data sets, I'll be able to do a comparative analysis of both to isolate the effects of the room acoustics on the array performance. And I also think that Ricardo is interested in looking at the some of the room acoustics plots that we'll come up with in the control room too. So that'll be fun to look at. So here's a summary of my goals for the thesis. It's divided into the two components: the wavefield synthesis performance measurements in both locations and the room acoustics measurements in both locations. And then once all this data is collected, complete the analysis of that data to compare the system performance in the different acoustic environments, and then determine and define the system's limitations, and then make informed recommendations on potential improvements to the system or to the room acoustics of the lab. So identifying some potential limitations to this research. If we're using a single microphone for measurement, that could have some limitations. No HRTF was intended to be used, and then also phase matching. So I'll go into each of these. Single diaphragm condenser measurement microphones are accurate, but they don't fully recreate the experience of human hearing. So we could enhance this acoustic research by using a binaural measurement microphone. Ideally, it's one of those, like those Neumann heads that I showed earlier, that with microphones attached to the ears of a mannequin head. And that would ensure the accurate representation of the binaural human hearing. So We're in the process of acquiring a binaural microphone or a microphone array or even one of these mannequin heads. So if that's acquired within the scope of the timeline of my thesis, I'll be using that in addition to the single diaphragm measurement microphones. But if not, it'll just be this single microphone placed at numerous locations. Also, we weren't intending to use HRTF for the data analysis, which head-related transfer functions. That's the response that characterizes how the ear receives audible sounds, considering the ear shape and reflections off the head. This filter can be applied to mono stereo recordings to recreate the sound that an ear would be receiving, but this would complicate the computation and data analysis, although it would provide better representation of the human hearing, but there's no intention of using AHRTF on this data at this moment in time. And then also phase matching. So phase matching, as probably a lot of you know, is a common technique that's used in audio recording that ensures two microphones that are recording the same source. So say a snare drum, for instance, there's two microphones miking one snare drum. You want those mics to be receiving the snare sound with the same phase, because whenever you mix those down, they could cause unwanted destructive interference if they're out of phase from each other, right? And summation of these two waves lead to silence, right? So a common solution is to just place the microphones equidistant from the source, and then you're basically ensuring that you're getting the same phase in both, and then you won't get this destructive interference. So that's phase matching. Phase matching is also a factor when you're talking about transducers in an array, like wavefield synthesis. So this transducer should be phase matched. And if they aren't phase matched, you can get these similar destructive interference effects. And some aspects of the phase are determined by like the innate characteristics of the system's components, like the electromagnetic properties of the magnet within the speaker, or the wire and the length of the wire and the resistance and all of these other things. So it's difficult and a little bit out of our control. But some things, if we can control it, we would like to. But just understanding and realizing that this unmatched phase could damage the spatial performance and affect the data is something that I'm considering too with this research. So a little timeline. By the end of the month, I would like to complete the testing, the design of the experiment, and the measurements within the spatial experiences lab, and also complete the room acoustics measurements so that I can then replicate those in the week or two after spring break in the beginning of March. And I'll do that in the Vlahakis studio. And then I'll spend the month of April kind of analyzing this data, collecting it. If there's any holes in the data, I guess I can use that time to reproduce some of those measurements. And then by the end of April, doing the defense and submitting the final paper as well. And, we may need some extra hands when we're doing some of these measurements. So if any of you are interested in doing that, feel free to reach out. And or if anybody even just wants a tour of the lab or anything, or wants to hear the system, that'd be great too. Just let me know. And in conclusion, I plan to do this foundational study that will guide the future work in the spatial experiences lab using the array. And this combination of loudspeaker measurements with the room acoustics measurements will help us obtain a holistic understanding of the system's performance that can be used not only in scientific experiments applications with this array, but also music and art and any other applications that are using the array. So that's the end of my presentation. Thank you for your time and for listening. And if anybody has questions or suggestions on the work at this moment, feel free to let me know. Thank you, though.
I have a question, John.
Sure.
In the studio, recording studio, I think you mentioned something about potential improvements. I don't know if it related to that bullet related to that.
Yeah. So
what would you envision for that?
Yeah, sure. Honestly, that room sounds really good already. I think that the potential improvements would definitely be more related to the spatial computing lab because it's such a boomy room. But if I were to predict what kind of improvements would need to be in there, I'd be curious how the stuff in the room affects. Like I remember I was in there when Ricardo got the new big screen that's on the right in the room there, and he was like, it was throwing him off when he was listening. You know, he was like, he had to tune his ear to figure out, you know, how that was affecting it and how it was making a difference. So I'd be curious to see how, depending on how many people are in the room, depending on what chairs are in there and other things, how that affects it. But for the room itself, you know, I think those diffusion panels on the back and the general shape of the room are already doing a very good job. But, you know, maybe we'll see something in the acoustic data that tells us otherwise, and we analyze it and we see that there's a treble frequency in there, or there's some kind of reflection that we don't want, and then we can treat it as we see fit. But I think it already sounds really good in there.
Well, do you have a premeditative boundary conditions where you start like the room in this condition with people and and then iterate? Or how does it work in general?
Yeah, so I mean, anything that's in the room is going to affect how it sounds, like blanket statements.
And how
So
do you start? Where do you start?
yeah, I mean, if I were to start, I would just say, like, what's the most common use case of the room? Like, what's the average size of the class in there? And then
Okay.
maybe I would, you know, start from there, you know, because it's however it's going to be used most, that's how it should sound best. But
Okay.
that's where I would start. But you know, you can really go very detailed.
Okay. My second question: Are you
Sure.
going to use the Shep mics at all in this experiment?
I don't intend to. So those Shep's mics are really good for recording. But recording microphones don't necessarily have a flat frequency response because that doesn't always sound the best. So a lot of companies manufacture specific measurement microphones that are condensers, just like the Shep's are, but they're more flat in their frequency response. So because they're flat, they kind of give better acoustic data. So the Shep's, I would say, are more for recording music and audio in general, and then we would use some dedicated measurement microphones.
I think they're 155 degrees. Do you know why that is?
So I thought it had something to do with the ears, but I could be wrong.
Okay, so I want to chime in for a second here.
Sure.
The angle of the Shep's stereo mic is 100 degrees.
100 what?
Is 110, and that's important because I know a lot of people say that they think it's the same distance apart of those two mics, the same distance as the ears, but this is really not the reason that it works so well. That angle of 110 is important because a cardioid mic, a true cardioid mic, or true condenser cardioid mic, when it's off axis by 55 degrees, it's 3 dB down. And you take those two mics and send them off axis in each direction by 55 degrees, you're 3 dB down to the left and 3 dB down to the right. And that's exactly the definition of center channel. So really that stereo mic gives you three things. It gives you a left, a right, and a center. And it's that angle of 110 degrees that's so important for that.
Okay, thank you.
Now, just John, the other day we were talking about frequency responsive mics, and one of my students pulled up the graph of that ORTF Shep's mic. It was a straight line from beginning to end, all the way across. Now I know that it's a little complicated because you have so many reflections in the room that can alter that, and they didn't test that mic in our room. So it's, you know, sure, I know they have calibration mics that probably are more useful in some ways. I just want to say one other thing about this room. This room is what they call LEED, L-E-D-E. It has nothing to do with LEED, which is environmentally sound room. But LEDE means live end, dead end. And therefore, I think the philosophy behind this is that the sound is different coming from the speakers out than it is from the back of the room going forward. So I think one interesting thing in your experiment would be to put that speaker array facing one direction and then facing another direction, and to see how well that design, or if that design even works in real life. There was one other thing, and that was, okay, about the sound of the room itself. We never really calibrated this room from the loudspeakers. And I think that's where you can help us out with that, to see if the loudspeakers give a peak in the room that we can, or, a valley in the room that we could adjust.
Very cool. Yeah, I'd be happy to help. Yeah, and that makes sense because you have all those diffusers in the back. It would definitely make a difference because if you're pointing towards those
Panels
diffusers.
on the ceiling all aimed in that direction,
Yeah,
and
true. Yeah.
the left, which keep the sound moving in one direction, and then it's diffused when it hits the panels on the back.
Right.
Yeah, the live end dead end idea is that when you're in a listening environment, you don't want a completely dead room, right? I mean, that's not really the way you want to listen, but you also don't want to manufacture reflections coming off the back wall and then hitting the front wall again. So the front wall tends to be padded, with the exception of the window that you have between the studio and the control room. But the back has the diffusers to break the sound up so that you don't get direct parallel reflections going back toward the front of the room as well. But you still get a little bit of live ambience in the room when you're listening, when you're in the room.
Definitely don't want a dead room.
I was going to ask you, Ricardo, if back in the day, Greg Visa had actually done any measurements in the room when it was finished, but I guess the answer is no. So
if he did, I'm not aware of it, but he has a pretty good ear, and I know that he used his ear in the other side of the glass, and told me that there was a peak at a certain frequency, and every time I do a recording, I find a peak at that frequency that he mentioned. And we're in the process now of changing the sound of the live room. Thanks to Christian Chechko, we found some of those diffusers in the basement under Kresge that no one wanted, and we decided to use them. They're very expensive and they're in very good condition. And we also got some absorption panels to go between those diffusers. So we'll see, we're in the process now of putting that together, and we'll see how that works for the live room.
Rich has a question.
Yeah. Thank you, John. John, first off, thank you very much. I think it's a really good presentation. Very well organized. I love the graphics and the videos and everything. Really good. I had a couple of really small questions that I'm almost afraid to ask because they feel like I'm nitpicking.
No, it's fine.
Nevertheless, I'm curious anyhow. Toward the end of the show, you mentioned a couple of limitations / drawbacks. One of them was binaural sound, and the other was in phase matching.
Sure.
On the binaural sound side, you raised a question about HRTFs, and then suggested that by using binaural microphones, you'd be able to get the information. I wonder about that because, as I know you know, the HRTFs are intended to represent the transfer function from the sources to the eardrum, including everything. Right. And I always thought that those ear-mounted microphones kind of block out a lot of that stuff. They certainly cover the pinout, and it seems that a lot of the activity and the interest in the HRTF community is centered around the importance of individualized HRTFs to get naturalistic response. So, any thoughts or comments on that?
Yeah, and I don't know. I think so. In general, the main motivation for the study was just the fact that they're going to Dr. Heller and Dr. Rosenberg will have human subjects in there to listen. So if it's not a personalized HRTF, but it is like a general one, then maybe it would give them some intuition on how that system is actually how once you put human ears in there instead of a microphone, how it's actually going to alter the perception of the system. So even if it's not personalized, it might just improve their understanding of what stimuli they're going to use for the experiment and what other aspects of the experiment. So I didn't intend to use an HRTF, but I think that they're both of my co-advisors, who are Dr. Rosenberg and Dr. Heller, are leaning towards having some type of a binaural measurement, just because it will be a human subject test. So, but actually, Dr. Heller mentioned that you may have some type of binaural microphone as well. specifically? Like, what do you have one of those key Mars, or does anybody have one of those key Mars? That,
We don't. Never did.
okay.
We had something else for a while that was a mannequin, but it was not really a professional key mark.
Gotcha. Yeah, those are expensive. But yeah, we were looking at acquiring some kind of binaural mic possibly, and then comparing that to the single microphone data and seeing how different they were as well.
The other question that I had, and I don't want to take up too much airtime.
Sure.
The other question that I had concerned the phase matching. You state quite correctly how and why that's an important thing to worry about. I always wonder that with real, normally not manufactured to be matched hardware. First off, how much control you're going to have, especially at the high frequencies,
right,
where the wavelengths are short, and it's moving it around a little bit, can really muck up the phase.
Right.
And also, I don't know the mics that you're using, but are the phase characteristics really predictable and consistent across frequencies? And if they're not, then you'll have to compensate really using other means besides just simply moving the microphones. On the other hand, I'm not sure how much it matters, especially, but it will make a difference for all the reasons that you stated.
Sure. Yeah, and I'm curious too, the high frequencies will be more affected like you just said, but if there's going to be spatial aliasing at a lower frequency anyway, due to the spacing of the speakers, which I think right now we're predicting using the formulas that the spatial aliasing was going to be around like 2K, if I remember correctly. So I don't know how we're going to handle that, if we're going to decide to, whenever they're using the stimuli in the experiments, if they're not going to use anything outside of that aliasing frequency. And if those are the treble frequencies for the phase matching, then maybe it just doesn't matter in general. So we'll see. But thank you for the tips, and I'll be in touch offline because I have a couple more questions for you, I think, follow up to that. So thank you.
Are there any other questions?
I had one. You had mentioned the lab that used it was at the Arup lab, maybe?
Arup, yeah.
I didn't catch, are they mimicking sound treatments in there, or are they moving the array to different rooms to test? Well, I didn't understand the overall.
Yeah, so Arup, I worked there over the summer as an intern, and basically they have a spatial audio room called the Sound Lab that has ambisonics and wavefield synthesis in it, and they'll go into a space and they'll get an impulse response of a space, or they'll get an impulse response from their 3D model, an acoustic simulation model, and then they'll pump that into the system, and then you can sit in there and hear what would a conversation sound like, what would music sound like if I were sitting in this room, and they can do that before they actually construct the space or actually renovate the space. So it's useful in the architectural acoustics world. I don't know if that answers your question there.
Yeah, they're mimicking the space that they're thinking about.
Yeah, they're mimicking the space, or maybe it's already a space. Like they'll take an impulse response of an already existing space, and then they'll say, "This is what would happen if we put foam on the walls," or something like that.
Cool.
Yeah.
Any
other questions?
Okay, well, once again, John, thank you so much for doing this, and I certainly look forward to seeing that array in the Lahonkus recording studio.
Yeah, it'll be fun. Thank you. Have a good one.
Stop recording.